Yes, welcome all to the online classes, subject engineering physics, and today's topic is fiber optics, run in the BTech Agriculture first semester. An optical fiber, the fiber optics or optical fiber is essentially a waveguide for light. It consists of a core and cladding that surrounds the core. The index of refraction of the cladding is less than that of the core, causing rays of light leaving the core to be reflected back into the core. So here are the laws of reflection or refraction, or the physics of wave theory is applied in the working principle of fiber optics. A light emitting diode, LED or laser diode can be used for the source. Advantages of optical fiber include it's had greater bandwidth than copper wires, lower losses, immunity to crosstalk, no electrical hazards. Now, before moving to the detail, I just give the brief introduction of the fiber optic. That is, in the 21st century, the era of information technology, there is no doubt that information technology has had an exponential growth through the modern telecommunication system. Particularly, optical fiber communication plays a vital role in the development of high quality and high speed of telecommunication system. Today, optical fiber are not only used in telecommunication links but also used in the internet and local area networks to achieve high signaling rates. So, history perspective of optical fiber communication in the use of light for transmitting information from one place to another is a very old technique. In 1800 BC, the Greek used fire and smoke signals for sending information like victory in a war or war alerting against enemy. Call for help, etc. Mostly only one type of signal was conveyed. During the 2nd century BC, optical signals were encoded using signaling lamps so that any message could be sent. There was no development in optical communication till the end of 18th century. The spread of the optical communication link was limited due to the requirement of line of sight transmission path. The human eye as the receiver and unreliable nature of transmission path affected by atmospheric effects such as fog and rain. In 1971, Chappé from France developed the sea shore for telecommunication on land, but that was also with limited information transfer. In 1935, around 1935, Shmai Moore invented the telegraph and the era of electrical communication started throughout the world. The use of the cables for transmission of Morse coded signals was implemented in 1844. In 1872, Alexandria Graham Bell proposed a photophone with diaphragm giving speech transmission over distance of 200 meters. But within 4 years, Graham Bell had changed the photophone in the telephone using electrical current for transmission of a speech signal. In 1978, the first telephone exchange was installed at New Haven. Meanwhile, Hertz discovered radio wave in 1887. Marconi demonstrated radio communication without using wires in 1895 using modulation techniques. The signal was transmitted over a long distance using radio waves and microwave as the carrier. During the middle of the 20th century, it was realized that increase of several orders of magnitude of bit rate distance product would be possible of optical waves were used as the carrier. So there are certain systems like old optical communication, telegraph, telephone, coaxial cables, microwaves, laser light in open air. The bit rate for old optical communication is 1 bit per second. Telegraph 10 bit, telephone 10 to the power 3, coaxial cables 10 to the power 5, microwaves 10 to the power 6, and laser light in open air is 10 to the power 9. So different communication system and their bitrate distance products. Here the repeater spacing is mentioned as the distance. Okay. So the communication engineer were interested in optical communication using laser in an effective manner from 1960 onwards. A new era in optical communications started after the invention of laser in 1960 by Myman. The light waves from the laser, a coherent source of light wave having high intensity, high monochromaticity, and high directionality with loss divergence and use less divergence are used as carrier waves capable of carrying large amount of information compared with the radio waves and microwaves. Now, unguided optical communication. The optical communication system and different from microwave communication system in many aspects. In case of optical system, the carrier frequency is about 100 terahertz and the bit rate is about 1 terabit per second. Further, the starting of optical beam is always in the forward direction due to the short wavelengths, even though it is not suitable for broadcasting application. It may be suitable for free space communication above the Earth atmosphere like interterrestrial communication. For the terrestrial application, unguided optical communications are not suitable because of the scattering within the atmosphere, atmospheric turbulence, fog, rain. Unguided optical communication system played an important role in the research between 1960 and 1970. For longer range unguided optical communication system at the nano domain laser 1.05 micrometer and the carbon dioxide laser 10.6 micrometer were the most favorable sources using narrow band gap compound semiconductors like indium sulfide and cadmium mercury telluride. One can have better detection using heterodyne and detection technique. Now the birth of optical fiber system or optic system. During 1950, the optical fibers with large diameter of about 2 millimeter were used in endoscopes to see the inner parts of the human body. Optical fibers can provide a much more reliable and versatile optical channel than the atmosphere. Kao and Hockham published a paper about the optical fiber communication system in 1966. But the fiber produced an enormous loss of 100 dB per kilometer, but in the atmosphere there is a loss of few dB per kilometer immediately. So, this is the structure of optical fiber and this is the block diagram of optical fiber communication system. A signal source, copper cable, optical transmitter, then optical fiber optic cable, optical receiver, copper cable, and signal destination. So, from optical transmitter to optical receiver, optical fiber cable is connected, and this optical transmitter carries the electrical signal and transmit or convert the electrical signal into the light signal, and that light signal travels through the fiber optic cable in a very fast speed compared to the copper cables and receive at the optical receivers, and again the decoded that light signal into the electrical signal and transmitted through copper cable to the signal destination. And this is the cross sectional view of the optical fiber, in which the centermost is known as the core and the intermediary part is known as the cladding and the uppermost part is known as jacket sheet. Optical fiber is made from thin strands of either glass or plastic. It has little mechanical strength, so it must be enclosed in a protective jacket. Often, two or more fibers are enclosed in the same cable for increased bandwidth and redundancy in case one of the fiber break. It is also easier to build a full duplex system using two fiber, one for transmission in each direction. Total internal reflection. Optical fiber work on the principle of total internal reflection. That is, we had studied in the wave theory, the total internal reflection is a phenomena, and this is the working principle of optical fiber. The optical fiber, with the light, the reflective index is listed. The angle of reflection at the interface between two media is governed by Snell's law. N1 sin theta 1 equals to N2 sin theta 2. Advantages of optical fiber. Optical fiber, as compared to copper wires, having the following advantages: a wide bandwidth. The information carrying capacity of the transmission system is directly proportional to the carrier frequency of the transmitted signals. The optical carrier frequency is in the range of 10 to the power 13 to 10 to the power 15 hertz, while the radio wave frequency is about 10 to the power 6 hertz, and the microwave frequency is about 10 to the 9 hertz. Thus, the optical fiber yields greater transmission bandwidth than the conventional communication system, and the data or number of bits per second is increased to a greater extent in the optical communication system. Further, the wavelength division multiplexing, WDM. Multiplexing, here the word multiplexing is used, and multiplexing means the simultaneous transmission of many signals through a single channel is known as multiplexing, and it is of three types. First is frequency division multiplexing, second is time division multiplexing, and the third one is the wave division multiplexing. So further, the wave division multiplexing operation by the data rate or information carrying capacity of the optical fiber is enhanced to many orders of magnitude. Low transmission losses. Due to usage of the ultra low loss fibers and the herbarium dropped silica fibers as optical amplifiers, one can achieve almost lossless transmission. In the modern optical fiber telecommunication system, the fibers have transmission loss of 0.002 dB per kilometer. Further, using iridium doped silicon fiber over a short length in the transmission path at a selective point, appropriate optical amplification can be achieved. Thus, the repeater spacing is more than 100 km. Since the amplification is done in the optical domain itself, The distortion produced during the strength ending of the signal is almost negligible. Dielectric waveguide. Optical fibers are made from silica, which is an electrical insulator. Therefore, they do not pick up any electromagnetic wave or any high current lightning. It is also suitable to explosive environments. Further, optical fibers are not affected by any interference originating from power cables, railway power lines, and radio waves. There is no crosstalk between the fiber, even there is so many fibers in a fiber cables because of the absence of optical interference between the fiber. So this is the important advantage that there is no crosstalk. Signal security. A transmitted signal through the fiber does not radiate. Further, the signal cannot be tapped from a fiber in an easy manner. Therefore, optical fiber communication provides 100% signal security. Small size and weight. Optical fibers cables are developed with small radii and they are flexible, compact and lightweight. Fiber cables can be bent or twisted without damage. Further, the optical fiber cables are superior to the copper cables in terms of storage handling, installation, and transportation, maintaining comparable strength and durability. No physical electrical connections required between the sender and the receiver. And as fibers are very good dielectric, isolation coating is not required. Next, refraction and total internal reflection. So the phenomena of refraction and total internal reflection are shown in the slides. Angle of incidence less than a critical angle. In second diagram, angle of incidence equal to the critical angle. Angle of incidence is greater than a critical angle. So when the angle is incidence is less than critical angle, then the refraction takes place, and if it is less or it is greater than critical angle, then reflection takes place. One terminology, numerical aperture, is used in optical fiber. The numerical aperture of the fiber is closely related to the critical angle and is often used in the specification for optical fiber and the components that work within it. The numerical aperture is given by the formula Na is equals to N1 square minus N2 square to the whole root. The angle of acceptance is twice that given by the numerical aperture. Modes and materials. Since optical fiber is a waveguide that light can propagate in the number of modes, if a fiber is of large diameter, light entering at the different angles will excite different mode, while narrow fiber may only excite one mode. Multimode propagation will cause dispersion, which results in the spreading of pulses and limits the usable bandwidth. Single mode fiber has much less dispersion but it is more expensive to produce. Its small size, together with the fact that its numerical aperture is small than that of multimode fiber, make it more difficult to couple to the light sources. So, according to the classification of optical fiber, there can be various classification of optical fiber depending on different parameters. We'll consider one by one. Classification of optical fiber depending on number of modes. There are two number of optical fibers depending upon the number of modes propagating into the fiber. Multimode step index fiber. Multimode step index fiber may be fabricated from either multi-component glass compounds or doped silica. These fibers can have reasonably large core diameters and large numerical apertures to facilitate the efficient coupling to an coherent light source, such as LED. The performance characteristics of this fiber type may vary considerably depending on the material used and the method of preparation. The doped silica fiber exhibits the best performance. A typical structure for a glass multimode step index fiber will show in the next slide. Now, almost the structure core diameter is 50 to 400 micrometer. Clad diameter is about 125 to 500 micrometer. Buffer jacket diameter is about to 250 to 1000 micrometer. And the numerical aperture is 0.16 to 0.5. Now the performance characteristics attenuation 2.6 to 50 dB per kilometer at wavelength of 0.85 micrometer, limited by absorptions or scattering. Now multimode graded index fiber. These multimode fibers which have graded index profile may also be fabricated using the multi-component glasses or doped silica. However, they tend to manufactured from materials with high parity than majority of multimode step index. Fiber in order to reduce fiber losses. The performance characteristics of a multimode graded index fiber one therefore generally better than those of multimode step index fibers due to index grading and lower attenuation. Multimode graded index fiber tend to have a smaller core diameter than multimode step index fiber. Although overall diameter include the buffer jacket is usually about the same, the typical structure is illustrated. That is, core diameter is 30 to 100 micrometer, clad diameter is 100 to 150 micrometer, and the attenuation is 2 to 10 dB per kilometer at the wavelength of 0.85 micrometer, with generally a scattering limit. Bandwidth 300 megahertz kilometer to 300 gigahertz kilometer. Application these fibers are best suited for medium haul, medium to high bandwidth application using in coherent and coherent multimode source, LED and injection laser respectively. Now single mode fiber. Single mode fibers can have either a step index or gradient index profile. At present, commercially available single mode fiber are still usually step index. They are high quality fibers for wide band, long distance transmission, and are generally fabricated from doped silica in order to reduce attenuation. Now, single mode fiber has much less dispersion but is more expensive to produce. Its small size, together with the fact that the numerical aperture is smaller than that of multimode fiber, make it more difficult to couple to the light sources. Types of fiber, I had already given that brief review. Both types of fiber described earlier are known as step index fibers because the index of reflection changes radically between the core and cladding. Graded index fiber is a compromise multimode fiber, but the index of refraction gradually decreases away from the center of the core. Graded index fiber has less dispersion than multimode step index fiber. These are the some pictorial representation of graded, multimode, and step index fibers, in which their core diameter is varying, and I had discussed the advantages of each of the type of fiber. Now, dispersion in fiber optic results from the fact that in multimode propagation, the signal travels faster in some mode than it would in others. Single mode fibers are relatively free from dispersion except for intramodal dispersion. Graded index fiber reduce dispersion by taking advantage of higher order modes. One form of intramodal dispersion is called material dispersion because it depends upon the material of the core. Another form of dispersion is called waveguide dispersion. Dispersion increases with the bandwidth of the light source. Now, example of dispersion. If white light is fall on a prism, then a dispersion of white light gives the two light, violet and red. So the original signal and the dispersed signal is shown in the slide through the mode of figures. The fabrication processes the fabrication process of fiber optics are done by vapor phase oxidation technology. Today's fiber fabrication process include two major stages. The first stage produce a performa cylinder of silica composition 10 to 20 centimeter in diameter, about 50 to 100 centimeter long. This performer consists of a core surrounding by clad with a desired refractive index profile, a given attenuation, and the other characteristics. In other words, this is desired optical fiber, but not on a much larger scale. Outside vapor phase deposition or chemical vapor phase deposition method, modified chemical vapor deposition MCVD method, uh, and one of the most important fiber optical fabrication process is plasma activated chemical vapor deposition PCVD, and the one is vapor axial deposition method. This vapor axial deposition method was developed in 1977 by Japanese scientists. Depositing the glass particles which were obtained from reaction among gases in heated zone occurs at the bottom end of the target or seed or rod that rotates the moves upward. This deposition form a porous perform, the upper end of which heated in the ring furnace to produce a glass performer. So losses in optical fiber result from attenuation in material itself and from scattering, which causes some light to strike the cladding at less than critical angle. Bending the optical fiber too sharply can also Bending the optical fiber too sharply can also causes losses by causing some of the light to meet the cladding at less than the critical angle. Losses vary greatly depending upon the type of fiber. Plastic fiber may have losses of several hundred decibel per kilometer. Graded index fiber, multimode glass fiber has loss of about 2 to 4 dB per kilometer. Single mode fiber has loss of 0.4 dB per kilometer or less. Types of losses: relative loss, wavelength. I had already discussed the banding of the fiber gives the losses. You see in the figure or in the slide, light escape through the core cladding interface if the critical angle changes. There are two basic type of fiber optical cable. The difference is whether the fiber is free to move inside a tube with a diameter much larger than the fiber or is inside a relatively tight fitting jacket. They are referred to as loss tube and tight buffer cables. Both methods of constructions have disadvantage or advantages. Loss tube cables, all the stress of cable pulling is taken up by the cable strength members and the fiber is free to expand and contract with temperature. Tight buffer cables are cheaper and generally easier to use. Fiber optic cable construction. So, loss tube construction and tight tube buffer construction is shown. The innermost part is core, the yellow one is cladding, and the shaded gray is fiber buffer, air or gel, then tube. So this is loose tube construction. Now, tight buffer construction, core, cladding, fiber buffer, plastic buffer, Kevlar strength membrane or member, and the uppermost part is plastic jacket. Thank you. Now some questionnaires need to be discussed. I'll show you. Just wait a minute. Now, some more slides which need to be discussed related to the fiber optic. Advantages of fiber. Fiber has three advantages compared with the metal wires: bandwidth, more data rate per second, longer distance, faster. Special applications like medical imaging and quantum key distributions are only possible with fiber because they are use light directly. These are the elements of fiber data link: transmitter emit light pulses, LED or laser, connectors and cables passively carry the pulses, receiver detects the light pulses, transmitter cable, receiver. Repeaters for long link repeaters are needed to compensate for signal loss. Fiber, repeat, fiber, repeat, fiber, repeat, fiber, repeat, and so on. Optical fiber, core, glass or plastic with higher index of refraction than cladding. Carries the signal. Cladding, glass or plastic with lower index of refraction than the core. Buffer protects the fiber from damage and moisture. Jacket holds one or more fibers in a cable. Single mode fiber. Single mode fiber has core diameter of 8 to 9 microns, which only allows one light path or mode. Multimode step index fiber. Multimode fiber has core diameter of 50 or 62.5 microns, sometimes even larger. Allows several light paths or modes. This causes modal dispersion. Some modes take longer to pass through the fiber than other because they travel a longer distance. Multi-mode graded index fiber. The index of refraction gradually changes across the core. Mode that travel further also move faster. This reduces modal dispersion, so the bandwidth is greatly increased. Step index and graded index fiber. Step index multimode was developed first, but rare today because it has a low bandwidth, 50 megahertz kilometer. It has been replaced by graded index multimode with bandwidth up to 2 gigahertz. Plastic optical fiber, large core, 1 millimeter, step index multimode fiber, easy to cut and work with, but high attenuation. 1 dB per meter makes it useless for long distance. Sources and wavelengths. Multimode fiber is used with LED sources at wavelength of 850 and 300 nanometer for slower local area network. Laser at 850 and 1310 nanometer for networks running at gigabytes per second or more. Single mode fiber is used with laser source at 300 and 1550 and nanometer. Bandwidth is extremely high, around 100 terahertz per kilometer. Fiber optic specifications. These are the some fiber optic specifications which we had discussed. That attenuation, loss of signal measured in decibels. Dispersion, blurring of signal affects bandwidth. Bandwidth, the number of bits per second that can be sent through the data link. And the most important, numerical aperture, measure the largest angle of light that can be accepted into the core. Attenuation and dispersion. Attenuation is expressed in decibels per kilometer. Dispersion, distance, dispersion expressed in PS per. Measuring bandwidth. The bandwidth distance product in units of megahertz into kilometers shows how fast data can be sent through a cable. A common multimode fiber with bandwidth distance product of 500 megahertz can carry a 500 megahertz signal for 1 kilometer or 1000 megahertz signal for 0.5 kilometer. If the core and cladding have almost the same index of refraction, the numerical aperture will be small. This means that light must be shooting right down the center of the fiber to stay in the core. Fiber types and typical specification. These are the fiber types: 50/125 microns, 51/125 microns, 62.212 microns, 100.11 microns. This. Core cladding ratio are like this. And these are the some specification in regard of attenuation, bandwidth, applications, nodes. Popular fiber types. As there popular fiber types, at first there were only two common types of fiber: 62.5 micron multimode intended for LED and 100 Mbps network. There is a large installed base of 62.5 micron fiber, 8 micron single mode for long distance or high bandwidths requiring laser sources. Corning SMF28 fiber is the largest base of installed fiber in the world. Links. Gigabit Ethernet 62.5 micron multimode fiber did not have enough bandwidth for Gigabit Ethernet. 1000 Mbps. LEDs cannot be used as source for Gigabit Ethernet, they are too slow. So Gigabit Ethernet use a new inexpensive sources, vertical cavity surface emitter lasers. Multimode fiber designed for VCSELs. First came laser rated 50 micron multimode, bandwidth 500 MHz, kilometer 850 nanometer. Then come laser optimized 50 micron multimode, bandwidth 2000 MHz, kilometer at 850 nm. Distinctive aqua colored jacket. You can't make single mode and multi-mode fiber. You lose 20 dB at the junction. So we cannot mix the fibers of different mode. Mixing 50 micron and 62.5 micron multimode is not as bad, but you lose 3 dB, half the power, which is usually unacceptable. Fiber manufacture. Three manufacture or fabrication. One is modified chemical vapor deposition method. Second is outside vapor deposition method and vapor axial deposition method. Modified chemical vapor deposition method MCVD. A hollow rotating glass tube is heated with a torch. Chemical inside the tube precipitate to form soot. Rod is collapsed to create a preform. Preform is stretched in drawing tower to form a single fiber up to 10 km long. Modified chemical vapor deposition, censored glass layer, soot deposition, glass, perform fabrication. Outside vapor deposition method, a mandrel is coated with porous perform in a furnace. Then mandrel is removed and the perform is collapsed in the process called sintering. Vapor axial deposition method, perform is fabricated continuously. When the perform is long enough, it goes directly to drawing tower. Drawing, the fiber is drawn from perform and then coated with protective coating. This is the phenomena. Index of refraction. Index of refraction. When light enters a dense medium like glass or water, it slows down. The index of refraction n is the ratio of the speed of light in vacuum to the speed of light in the medium. Water has index of refraction n equals to 1.3. Light takes 30% longer to travel through it. Fiber optic glass has n equals to 1.5. Light takes 50% longer to travel through it. Fiber applications, step index multimode, large core size, no so source power can be efficiently coupled to the fiber, high attenuation, low bandwidth, used in short, low speed data links, also useful in high radiation environments because it can be made with pure silica core. Next, graded index multimode, useful for premises networks like lanes, security systems, etc. 62.5 obliques 125 micron has been most widely used, works well with LEDs but cannot be used for gigabit Ethernet. 50 oblique 125 micron fiber and WOVSELS are used for faster networks. Single mode fiber, best for high speed and long distance, used by telephone companies and CATV. Fiber performance. So that is all for today. In next lecture, we are going to start with attenuation or fiber performances. That is starting from the attenuation and the losses and the efficiency and all that. So thank you to all of you.